Hey, welcome to our latest explainer. Today we're going to look past the big headlines and dive deep into the numbers that shape all that health news we see every day. We're on the hunt for this hidden influence that affects pretty much every study you read about. We're talking about the bias nobody sees.
All right, let's jump right in. You've probably seen a headline like this, right? New study finds coffee drinkers live longer. And it's so tempting to just think, awesome, coffee is a miracle drink. I'll have another cup. But is the story really that simple?
Or could there be something else going on? Some kind of invisible factor that's hiding in the data, just quietly clouding the truth and maybe leading us to a totally wrong conclusion. This is the exact question that biostatisticians wrestle with every single day. Well, that invisible influence actually has a name: confounding variables. The best way to think of them is like hidden suspects in a detective story. These are factors that are connected to both the thing you're studying, like drinking coffee, and the outcome, like living longer. So, for example, what if people who drink coffee also happen to exercise more? Is it the coffee making them live longer, or is it the exercise? That confusion right there is what creates a false association.
So, how in the world do we catch these hidden suspects and see through all this statistical fog? Well, researchers have this really powerful toolkit designed for exactly this. So let's open it up and see how they actually uncover the truth. Okay, our first tool is called propensity score methods. I know, it sounds super complicated, but the main idea is actually pretty simple. It's all about creating a fair comparison. This method looks at all of a person's characteristics, their age, their habits, their health, and then it calculates the probability, or propensity, that they would be a coffee drinker in the first place. This lets researchers find a kind of statistical twin for every person in the study, making sure the groups they're comparing are as similar as possible in every other way.
And check this out. This shows you just how powerful that is. On the left, before any matching, our group of coffee drinkers just happens to have way more people who exercise regularly. That's a huge confounding variable. But then look to the right. After applying these propensity scores, the groups are balanced. Now they both have a similar mix of exercisers. The suspect has been neutralized, which means any difference we see now is much more likely to be because of the coffee.
All right, let's grab our next tool. This one is absolutely critical for figuring out what works in the real world of medicine. It's called a dynamic treatment regime. Now, instead of some rigid, one-size-fits-all plan, think of this more like a choose-your-own-adventure for patient care. It's basically a set of rules that personalizes treatment over time by adapting to how a patient is actually doing. Here's a super simple example of how it works. A patient starts with the standard treatment, then after 6 weeks, doctors check in on their health. If they're getting better, awesome, they just keep going on that same path. But if they're not, the regime gives a clear rule. Okay, it's time to switch to the new treatment. This is how medicine can become truly responsive and tailored to the individual.
Now, every good detective runs into obstacles. And in data analysis, a massive one is missing data. These are just the gaps and holes in our information. It's like trying to solve one of those 1,000-piece puzzles, but a quarter of the pieces are just gone. If we just ignore those gaps, the final picture we put together could be completely wrong.
And believe me, this isn't a small problem. Just look at this chart. In this hypothetical study, a full 25% of the information is just missing. You wouldn't want doctors making a major health decision based on a study that's missing a quarter of its data, right? That's exactly why biostatisticians have developed some really clever techniques to account for this missing info, to reduce its power to mess up the result.
But what about the clues you don't even know exist? That's kind of the ghost in the machine of statistics, unmeasured confounding. This is the bias that comes from those hidden factors that weren't measured or maybe couldn't even be measured. Think about things like a person's stress level, their specific genetic makeup, or how strong their social support system is. These things have a massive impact on our health, but are incredibly difficult to capture.
So, to handle all this complexity, the confounders we know about, the missing data, and even those unmeasured ghosts, researchers pull out our final set of tools: nonparametric and semiparametric models. The key word to remember here is flexible. Instead of just assuming that the benefit of coffee is, say, a perfect straight line, these methods allow for more complex realities. Maybe coffee helps up to a certain point and then the benefits level off. These flexible models don't try to force the data into a simple box. They let the data itself tell the true, often messy story. So, we've looked inside the toolkit, we've seen the methods for dealing with bias, with complexity, with all of it. But what's the final verdict? I mean, why does all of this really matter for you and me?
And honestly, this is the whole ballgame. These methods are the difference between just seeing a simple correlation, like coffee drinkers live longer, and actually understanding the real cause and effect. They are the engine that powers evidence-based medicine, strengthening our trust that a study's findings are legit. And at the end of the day, all this rigorous work leads to smarter public health decisions that affect all of our lives.
Which, of course, brings us right back to where we started. The next time you see one of those bold new health headlines, just pause for a second. Remember the detective's toolkit and empower yourself by asking one simple but really critical question. What's the bias nobody sees?
Hey, if you found this deep dive into statistical bias useful, help us explain more stuff like this by liking and subscribing. And if there's some complex topic you want us to break down next, please let us know in the comments. We'd seriously love to hear from you. Thanks for watching.